So starting off here where we left off with the vanadium rainbow. When we ended yesterday, we actually ended the slides here on the color wheel speaking about the influence, right? The factors that influence the colors of transition metal ions, right? Which were the ligands, the types of ligands, whether it be strong field, weak field ligands, the oxidation state of said metal ion, and the geometry that it possesses, right? So that affects the color, right? But here we are now, the vanadium rainbow. No, the vanadium rainbow just display, it's just the name of an experiment that we tend to do with vanadium ions, as vanadium at different oxidation states tend to possess different colors. So its oxidation states creates a rainbow array of different types of colors. That's what we're describing, right? Yeah, that's really about it. Can anybody let me know what the atomic number of vanadium is? What's the atomic number?
23.
23. Lovely. All right. So it's in that first row, transition metal, right, that we're looking at. So the vanadium rainbow, as I said, it's just an experiment that demonstrates the variable oxidation states of vanadium, right? So the main oxidation states of vanadium that we'll look at are usually the plus 2, plus 3, plus 4, and plus 5 oxidation states, right? They produce a range of different colors at the high oxidation states, right? And that is what we really describe as a vanadium rainbow, that entire spectrum that is produced from vanadium, right? So let's have a look at this. So vanadium here, right? Vanadium yellow, right? At the starting point is usually ammonium vanadate, right? So we usually start from there, which contains vanadium at the plus 5 oxidation state. This leads to a yellow color which dissolves in acidic solution, right? So vanadium oxide as well, vanadia, right, is an organic compound with that formula there, right? This also possesses the brownish yellow vanadium plus 5 oxidation state, right? So we're just looking at the oxidation state of vanadium, and you need to know the color of each oxidation state, right? And a question that asks you for every single color of all the vanadium ions is on the 2021 paper, right? So it is something that the syllabus asks you for, right? So vanadium plus 5 tends to be this yellowish color, all right? And we have two compounds, ammonium vanadate and vanadium oxide, that possess this plus 5 oxidation state, all right? Vanadium blue now, here we have the vanadium plus 4. So after adding a reducing agent, you reduce vanadium from the plus 5 to the plus 4 state, and this results in this bluish color that we see here on the right, indicating the formation of the vanadate ions, right? And this is usually found in vanadyl sulfate, right? VOSO4, which is this bluish color, right? So plus 5 is going to be the yellowish brown or just yellow, and plus 4 is going to be blue. All right. Vanadium, the green one now, right? So continuing the reduction process, we're decreasing it from plus 4 to plus 3, and the plus 3 oxidation state is usually present within the regular vanadium ions, as the plus 3 oxidation state for vanadium is one of the most stable, and these are found within the compounds vanadium 3 chloride, right? Or vanadium trichloride. Hopefully that makes sense so far. Alright, it's really just relating the colors, so there's nothing to really understand, but it's just memorizing the colors of these. Alright, so this is a plus 3 oxidation state. For the plus 2 oxidation state now, further reducing it from plus 2 to plus 3 results in this purplish violet color of the vanadium 2 plus ion, which is also another stable oxidation state, so it can be found free floating, right? Commonly seen in dissolved or aqueous vanadium 2 chloride, right? So that tends to be purple. So we have that there. So that is what we have. So we're moving from +5, which is yellow, +4 is blue, +3 is green, +2 is purple, right? So those are different oxidation states of vanadium and the colors in which the colors of which they actually produce. Right? And it helps us drive home the point that the different oxidation states of the elements, right, in the transition in the D block rather, right, actually changes or can have an influence on the color of the compounds which they produce. All right. So +5 to +2, we have all the colors there. I'm not sure if there are any questions so far. All right. Doesn't seem to be. All right. The last piece that we're looking at here is the use of transition metals in redox reactions. Right? Can anybody give me some examples of transition metal compounds that we tend to use a lot in redox reactions? Which ones do you tend to see a lot? You see them all over in your titrometry. You see them all over within balancing your redox reactions, especially in acidic media. So, what are the transition metal ions that you tend to see within redox reactions?
Jay,
Mm-hmm. You're giving an example? I didn't hear an example. All right, so
no, before you went to that point, I think I saw somewhere, Mr. Scott,
go ahead.
I'm saying that I think I saw somewhere where they were saying like when before actually reaches purple. Because I was looking at a past paper yesterday afternoon, and instead of having the four colors, it had like 5, 6 lines.
All right. Hmm. Instead of having the four colors, you have five different. All right, so okay, we'll look at that. We'll have a look at that, and
Do
if
you
need
understand
be,
what I'm
no,
asking?
you're asking, right? Hold on, let me see. I'm hearing a lot of interference. Not sure what that is. Could you restate the question to make sure that I have absolutely the question that that you were asking? Could you restate it now?
I'm saying that I read somewhere where they were saying that before you reach from yellow to purple, you transition to 4 and 3 before you reach 2. Um, the 2+ oxidation state. But instead of going directly from green then to purple, there's like some changes. There's like a stage where there's a mixture of more than one oxidation state. So you have it
Mm-hmm.
like transition into this state, then goes back to this state before it actually reaches to purple. You understand what I'm asking?
No, yeah, I understand. All right. So when you're oxidizing it, when you're well, not oxidizing, when you're reducing it, you're adding a reducing agent to your vanadium complexes, right? All of it won't necessarily oxidize at once. And what you're saying is that sometimes the oxidation states can exist together that will create like a mixture of different colors, like a transitionary color, right? And sometimes it has to attain a different oxidation state before fully reducing rather back to vanadium 2 plus, right? So there are transition states that exist, right? Meaning that it's always the +5, 4, 3, 2, right? But sometimes there can be a mixture of them that will create probably an orangish color or something like that, right? So there can be mixtures that exist, right? Because if two oxidation states are existing within the same media, right, that will change the color of the medium specifically, right? But what I did here was treat specifically to the four oxidation states that we have to look at. We can discuss further as it relates to those transition states, right, between them, those different colors between them. But there is going to be like a room between two oxidation states where their colors are going to be somewhat mixed, right? Where more than one oxidation state exists in the one thing, right? But yeah, as I said, we can discuss more as it relates to that to see what those transitionary periods are and what ions are present within those mixtures to give the different colors that are not stated here. So you could discuss that. All right. A good thing to do would probably be to have a look at a YouTube video as they actually mix the vanadium with the different types of reducing agents and change the different colors, right? Because there is going to be a yellow, a green, there are going to be different shades of green, different shades of blue, right? When you add different reducing agents. For example, usually we tend to use zinc, right? So we could have a look at that, or I could send you guys a link to a YouTube video for you guys to look at the transitioning, how the colors transition, right, and the different colors that are within those transition states. Okay. All right. So that should be that. Is everything fine so far?
Yes, sir.
All right. So just remind me to send you guys a video as it relates to that. The creation of sodium vanadate and then moving from sodium vanadate down to vanadium 2 chloride or vanadium 2 chloride. All right, hold on. Use of transition metals in redox reactions, right? I was asking about this, but nobody was responding as it relates to the use of transition metals in redox reactions. So I guess I will just move on. All right. So we tend to see chromium ions, right? And I'm going to speak to the three different categories of ions that the syllabus asks for. So the chromium ion specifically, chromium 3 plus, right? The oxidation state 3 plus is relatively stable and acts as a reducing agent under certain conditions, usually in acidified media, right? So the role in redox reactions, the chromium 3 plus can be oxidized to higher oxidation states in reactions involving the permanganate ions as well. And it serves as an intermediate in the transition between a higher and a lower oxidation state of chromium, right? So usually chromium tends to be a great reducing agent, all right? So it's a good reducing agent generally. All right. Same thing for its dichromate ion, all right? We tend to use that as a strong oxidizing agent, right? So we have that there, right? Dichromate is commonly used to oxidize organic compounds and is used to can be reduced back to 3 plus in redox reactions, right? So classic use of this would be in your oxidation of alcohols that we will look at in unit 2, right? So our oxidation of alcohols are carboxylic acids generally, right? So usually we use that for that, and this is an example of what we use in the similar to what we do in the Jones test. You guys will have a look at that in unit 2. All right. So it's usually used to oxidize organic compounds.
In what test, sir?
You have the Jones test. There are different types of
What
tests.
test you said?
Jones, Jones. So it's similar to what is done in Jones test.
That sounds so unfamiliar.
Oh, it's unit 2 chemistry. So we wouldn't have looked at it before, right? But it's similar to
I
what
did
is done.
unit 2 last year.
Oh, you did unit
That
2.
is the problem.
The Jones test. Jones says so the alcohols, primary, secondary, and tertiary alcohol. Okay, never mind. Alright, it's there though. It is there. It is in my. There's a video right on that reactions of alcohols that I've done already. Right. So the iron ions. Now we know the iron ions already. We know our iron 3+, right? Our ferrous iron, right? So the role of the iron 3+, right? Generally, right, is to be used as typically with reducing agents like iodine, right? So we tend to use them, right, in analytical methods. So we tend to use iron to actually create complexes. Iron makes really good complexes, and we tend to use them in order to actually carry out some other reactions or use them as a catalyst, right? A Friedel-Crafts catalyst, that is also unit 2. So a lot of these uses are in organic chemistry, right? And they're also used in complexiometric titrations with what we call EDTA. Right, so complexiometry, we won't touch on anything close to that until Unit 2. It's not specifically done in Unit 2, but we can use it. Right, and we could probably have a look at it a little bit, or if anybody can make any relations to it when we're doing ligands. Alright. So it's usually used to create different types of complexes and used as a catalyst in a majority, in a good amount of our organic synthesis reactions, right? So that is it. And here we have iron 2+, which is our ferric iron, right? It is readily oxidized to iron 3+, making it useful in redox titrations. It's great for redox titrations, right? So it can be oxidized by dichromate or permanganate in acidified solutions. So we generally use it in redox titrations. All right. So you tend to see a blue, like a bluish green color, a dirty green color, right? And it changes to the brownish red as the titration comes to completion, right? So it's generally used in those redox reactions. And our manganese ions, which are very, very common. We tend to use manganese for almost everything, right? So our manganese 2+ can be oxidized to higher oxidation states, particularly the manganate ion, the MnO4-. The common use for the permanganate tends to be in titrations as well, as it acts as an endpoint indicator for by oxidizing it back to the manganate, right? So from 2+ to manganate. So this is what we tend to use it for in these types of reactions. All right, so redox reactions as well. Redox titration specifically. So we use these transition metal complexes all the time. Almost every single day in the lab for inorganic chemistry, we tend to use them. So for the manganate here, manganese in this +7 oxidation state, right, has this ion that is a very strong oxidizing agent, right? So as we stated before, right, it again is also used readily in redox reactions, right, and other types of chemical processes, right? So, right, we generally use it to find the endpoint of something, or we tend to use it to oxidize different things. For example, when we're dealing with organic compounds, when we're dealing with aldehydes and ketones and alcohols and those type of things, we tend to use them to create different types of substances, right? So because of it being a strong oxidizing agent, right, it can be used to drive reactions that otherwise would be extremely slow or just not feasible. All right. So, and we know that when we actually transition from the manganate to the Mn2+, we get a pale pink color, right? Purple to colorless or a pale pink color, right? So the manganate itself generally tends to be colorless, right? Well, the manganese ion tends to be colorless, right? And then it becomes purple in the permanganate form, right? Or it can become a pale pink color, right? If it is reduced, right? So just to make that sound less confusing, the manganese, depending on its concentration, it's going to have a colorless solution or a pale pink solution. When you oxidize it now, you're going to get a purple solution, which is the manganate, right? If it is reduced back to manganese ions, it's going to go back to colorless. So you guys need to know the oxidation states for the different types of metals that we tend to use, and you need to know their color changes as well. Right? So 7 plus state is purple, 2 plus state is pale pink or colorless, right? For the manganese. For the iron, 2 plus is green, 3 plus is red, reddish brown, right? And for the chromium now, right, we know that the chromium 3 plus is going to be orange, and the chromate itself, which is 6 plus, is going to be green, right? So you guys just need to know those colors, and it should be fine. All right? And the fact that almost all of them are just used simply as oxidizing agents, strong oxidizing agents, or in the case of iron 2 plus, tends to be a good reducing agent. All right? So that's really it there. Any questions? Any concerns?